Hello there, and welcome to this Sleepy Science channel. I'm so glad you found your way to this video because tonight we'll be exploring some of the most peaceful and fascinating facts about the cosmos. Wherever you are in the world, allow yourself to settle into this shared moment of stillness. Dim the lights, get comfortable, and let your body sink gently into your pillow. Take a slow breath and release the day's concerns. Tonight, we're drifting through the calming rhythms of the universe, where time moves with gentle patience and everything unfolds at its own peaceful pace. You'll discover facts that help you feel the quiet beauty of existence, the soft patterns woven through space, and the remarkable stability that holds everything together. These aren't dramatic revelations designed to shock or overwhelm. Instead, they're gentle truths that invite you to rest in the knowledge that the universe operates with a kind of serene predictability, a cosmic patience that has persisted for billions of years. Perhaps you've looked up at the night sky and felt a sense of peace wash over you. That feeling of being connected to something larger, something timeless and enduring. Tonight we'll explore why that feeling exists, and we'll let these calming cosmic truths carry you gently towards sleep. There's nothing you need to remember. Just let these thoughts drift through your mind like starlight filtering through evening clouds. Now, settle in as we begin this gentle journey through the most relaxing facts about the cosmos. When you look up at the night sky, you're not just seeing stars as they are now. You're witnessing light that has travelled across vast distances, carrying stories from the past. The light from many stars you can see with your eyes alone left those distant suns years, decades, or even centuries ago. This means that every time you gaze upward, you're looking back through time, observing the universe as it was, not as it is in this present moment. The nearest star system, Alpha Centauri, is about 4 light-years away, meaning its light takes over 4 years to reach your eyes. When you see that pinpoint of light, you're seeing it as it appeared 4 years in the past. This gentle delay connects you to cosmic history in the most intimate way. Consider Betelgeuse, the bright reddish star marking the shoulder of Orion. This stellar giant lies approximately 640 light-years from Earth. When you see Betelgeuse twinkling in the winter sky, you're observing light that began its journey during the late 1300s, long before modern civilization as we know it existed. The photons entering your eyes tonight left that star centuries ago, travelling silently through the vacuum of space, crossing incomprehensible distances to finally reach you in this quiet moment. Even more remarkable, some stars visible to the naked eye are thousands of light-years distant. Deneb, the bright star marking the tail of Cygnus the Swan, shines from about 2,400 light-years away. Its light departed that star around the time ancient civilizations were building their earliest monuments. That same light, unchanged and patient, continued through empty space, finally arriving here, now, to greet your gaze. This phenomenon transforms stargazing into a peaceful form of time travel. You're not seeing the universe as it exists in this moment. You're witnessing a collection of different moments, each star showing you its own particular fragment of the past. Some stars you see tonight may have already ended their lives, their light still journeying toward Earth, unaware that its source no longer exists. Others are surely still shining, steadily producing the photons that will reach Earth hundreds or thousands of years from now. There's something deeply calming about this realization. The light reaching your eyes tonight has been traveling for years or centuries, moving at 186,000 miles per second through the peaceful emptiness of space. Nothing can stop it. Nothing can slow it down. It simply continues, carrying its message across the cosmos until it finds an eye to see it, a telescope to capture it, or a surface to warm. This light is patient. It has all the time in the universe. When you look at the stars, you're participating in an ancient ritual that connects you not only to the distant past, but to every human who has ever looked upward and wondered. They saw different configurations, slightly shifted positions, but they saw the same light from the same stars, delayed by the same gentle cosmic intervals. And so the stars become bridges across time, linking past to present, connecting distant places to this quiet moment of contemplation. There's nothing you need to remember about these distances or these timescales. Just let the thought settle gently. You're looking backward through time whenever you look upward. The universe offers you this gift freely, every clear night, without asking anything in return. And so the ancient starlight continues to arrive, unhurried and eternal, connecting you to the vast history of the cosmos through the simple act of looking up. Beneath your feet, Earth rotates steadily through space at about 1,000 miles per hour at the equator. Yet you feel no motion, no jarring movement, only stillness and peace. This rotation is so smooth, so constant, that life has adapted to its rhythm completely. The spin of our planet creates the gentle cycle of day and night, a pattern that has repeated billions of times since Earth first formed. This predictable rotation allows you to rest each night, knowing that tomorrow the sun will rise again, the stars will return, and the cosmic clock will continue its patient ticking. The stability of Earth's rotation is one of the universe's most comforting constants, a reliable rhythm that cradles all life on our planet. At the poles, Earth's rotation slows to nearly nothing, while at the equator the surface moves at its maximum speed. Yet everywhere between, the rotation remains perfectly smooth. You might travel from pole to equator and never sense the change in speed. The atmosphere rotates with the planet. The oceans follow along, and everything on the surface moves together as one unified system. This is why you can sleep peacefully, why you can lie still and feel no dizzying motion, even though you're moving through space at remarkable speed. This rotation has been slowing down gradually over billions of years, but the change is nearly imperceptible. Each day lengthens by about 1.7 milliseconds per century. This means that when dinosaurs walked the Earth, days were slightly shorter, perhaps 23 hours instead of 24. The moon's gravitational pull creates this gentle braking effect through tidal interactions, but the change happens so slowly that no living thing notices it across its lifetime. The rhythm remains essentially constant, a dependable pattern that allows life to synchronize its internal clocks to the cycle of day and night. Plants have evolved to track this rhythm, opening their flowers at dawn and closing them at dusk. Animals, including humans, carry circadian rhythms that match the 24-hour cycle. Your body knows when to sleep and when to wake, guided by the steady rotation of the planet beneath you. This biological connection to Earth's spin has existed for hundreds of millions of years, linking you to the same cosmic rhythm that governed ancient life in Earth's early oceans. The rotation creates more than just day and night. It also generates Earth's magnetic field through a process called the dynamo effect. As Earth spins, the liquid iron in its outer core circulates, creating electric currents that produce a protective magnetic field extending thousands of miles into space. This field shields Earth from harmful solar wind and cosmic radiation, creating a safe haven where life can flourish. The rotation then does double duty. It provides the day-night cycle and maintains the magnetic shield that protects all living things. Perhaps you can imagine it now. You're lying still, resting peacefully, while the ground beneath you spins eastward at hundreds of miles per hour. The stars appear to wheel overhead, rising in the east and setting in the west, but they're not moving. You are. Earth is. And yet you feel only stillness, only peace. This is the gentle magic of living on a rotating sphere, the comfort of motion so smooth and constant that it feels like perfect rest. The rotation will continue long after this night ends, after countless nights end. Earth will keep spinning, maintaining its rhythm, providing its steady pulse for billions of years to come. There's deep comfort in this constancy, in knowing that the fundamental rhythms of your world are reliable and enduring. You can rest easy, held gently by Earth's rotation, cradled in its predictable cycle. Above you, stretching about 60 miles upward, lies Earth's atmosphere, a delicate blanket of gases that shields you from the harshness of space. This invisible layer protects you from harmful radiation, burns up most meteors before they reach the ground, and maintains the warm temperatures that make life possible. The atmosphere doesn't simply sit still, it circulates gently, distributing heat from the equator toward the poles, creating weather patterns and seasons. Every breath you take draws from this protective envelope, connecting you to a system that has nurtured life for billions of years. The atmosphere is thin when compared to Earth's diameter, yet it's remarkably effective, a cosmic guardian that allows you to rest safely beneath the stars. If you could see the atmosphere from space, you'd notice how thin it really is. Earth's diameter measures about 8,000 miles, but the atmosphere extends only 60 to 70 miles upward before fading into the vacuum of space. That's less than 1% of the planet's diameter. Yet this thin shell performs extraordinary work, filtering out harmful ultraviolet radiation from the sun, maintaining surface temperatures within a range suitable for liquid water, and providing the air pressure necessary for life as we know it. The atmosphere consists of layers, each with its own characteristics. Closest to the surface is the troposphere, where weather happens and where you spend your entire life. Above that lies the stratosphere, home to the ozone layer that absorbs most of the sun's ultraviolet light. Higher still are the mesosphere, thermosphere and exosphere, each becoming progressively thinner until the atmosphere finally merges with the near vacuum of space. These layers work together as a unified system, each contributing to the protective barrier that makes Earth habitable. Every day, Earth's atmosphere stops dozens of small meteors from reaching the ground. These rocky fragments, most no larger than grains of sand, enter the atmosphere at speeds of tens of thousands of miles per hour. The friction with air molecules heats them to incandescence, creating the brief streaks of light we call shooting stars. Most burn up completely, their atoms dispersing harmlessly into the upper atmosphere. Larger meteors may survive long enough to create spectacular fireballs before they too disintegrate. Only the largest objects ever reach the surface, and these are rare. The atmosphere acts as a constant shield, silently vaporizing space debris day and night, protecting the surface from bombardment. The atmosphere also regulates temperature through the greenhouse effect. Gases like carbon dioxide and water vapor trap heat radiating from Earth's surface, keeping the planet warm enough for life. Without this natural greenhouse effect, Earth's average temperature would be well below freezing, making the planet inhospitable to most forms of life. The balance is delicate but stable, maintained by natural cycles that have operated for billions of years. When you breathe, you're participating in ancient cycles. The oxygen you inhale was produced by photosynthetic organisms, plants and cyanobacteria that have been converting carbon dioxide into oxygen for billions of years. The nitrogen that makes up most of the atmosphere has been cycled through living things, rocks, and the air countless times. Each breath connects you to the entire history of Earth's atmosphere and biosphere, linking you to processes that stretch back to the planet's early days. The atmosphere moves constantly but gently. Prevailing winds circle the globe, carrying warmth from the tropics toward the poles and bringing cool air back toward the equator. These circulation patterns create Earth's climate zones, from the rainy equatorial regions to the dry subtropical deserts, from the temperate mid-latitudes to the polar ice caps. The patterns are predictable, following the same general paths year after year, creating the seasonal cycles that life depends upon. At night, the atmosphere continues its protective work. Even as you sleep, it absorbs cosmic rays, deflects solar wind particles channeled by Earth's magnetic field, and maintains the air pressure that keeps liquid water stable on the surface. This invisible guardian never rests, never falters, simply continuing its quiet protection of everything below. You can sleep peacefully, knowing that above you this delicate blanket of air stands between you and the harshness of space, a gentle barrier that has cradled life for billions of years. The moon, Earth's constant companion, hangs in the night sky about 239,000 miles away. This gentle presence does more than illuminate the darkness. The moon's gravitational pull creates the rhythmic rise and fall of ocean tides, a pattern that has shaped coastal life for hundreds of millions of years. Beyond the tides, the moon stabilizes Earth's axial tilt, keeping our planet's seasons moderate and predictable. Without the moon, Earth would wobble more dramatically, leading to extreme climate variations. Instead, the moon acts as a cosmic anchor, maintaining balance and allowing life to flourish in relative stability. Each night, whether visible or hidden behind clouds, the moon continues its patient orbit, a steadfast guardian in the darkness. The moon formed about 4.5 billion years ago, likely from debris ejected when a Mars-sized object struck the young Earth. From that violent beginning emerged a peaceful relationship. The moon settled into orbit, and over billions of years, tidal interactions gradually moved it farther away and slowed Earth's rotation. The moon currently recedes from Earth at about 1.5 inches per year, a gentle drifting that will continue for billions of years. Despite this slow separation, the moon will remain Earth's companion for the foreseeable future, continuing to provide its stabilizing influence. The tides the moon creates are predictable and rhythmic. Twice each day, the ocean rises and falls, responding to the moon's gravitational pull as Earth rotates beneath it. The sun contributes to tides as well, and when the moon and sun align, their combined gravity creates especially high spring tides. When they're at right angles, their pulls partially cancel, creating gentler neap tides. This pattern repeats every month, following the moon's phases with reliable precision. Coastal organisms have adapted to these rhythms, timing their reproductive cycles, feeding patterns and behaviors to the tidal schedule. The moon's gravitational influence extends beyond the oceans. It creates subtle tides in the solid Earth itself, raising and lowering the ground by several inches as the planet rotates. You can't feel this gentle flexing, but sensitive instruments can measure it. Even the atmosphere experiences slight tidal effects. The moon's gravity permeates everything on Earth, a gentle, omnipresent force that subtly shapes the physical world. Perhaps most important is the moon's stabilizing effect on Earth's axial tilt. Earth's axis tilts about 23.5 degrees relative to its orbital plane, creating the seasons. Without the moon, gravitational perturbations from other planets would cause this tilt to vary widely over millions of years, swinging from nearly 0 to more than 80 degrees. Such variation would create extreme climate instability, with ice ages and hot periods alternating unpredictably. The moon's substantial mass keeps Earth's tilt stable, varying by only about 1 degree over many thousands of years. This stability allows climate patterns to remain relatively constant, giving life the predictable conditions it needs to evolve and thrive. The moon also provides practical benefits. Its reflected sunlight illuminates the night, making nighttime navigation possible for countless species. Before artificial lighting, moonlight guided human activities during dark hours, providing enough light to travel, hunt, and gather. Many animals remain active during full moon nights, taking advantage of the extra illumination. Looking up at the moon, you're seeing a world that has remained largely unchanged for billions of years. Its surface preserves a record of impacts from the solar system's violent youth, craters that formed when asteroids and comets were more numerous. The dark patches, called maria or seas, are ancient lava flows that filled large impact basins billions of years ago. The bright highlands represent the moon's original crust, battered and fractured but still standing. This unchanging face has looked down on Earth since before life emerged, a silent witness to our planet's entire history. The moon will continue its orbit, maintaining its protective role, providing tides and stability, marking the passage of time with its phases. It asks nothing in return, simply continues its ancient dance, a cosmic partner that has shaped Earth's story from the beginning. Throughout the solar system, planets move along their orbits with remarkable precision. Earth circles the Sun once every 365 days, completing its journey with such consistency that we can predict its position thousands of years into the future. This orbital stability extends throughout the solar system. Jupiter takes about 12 Earth years to complete one orbit. Saturn takes nearly 30. These vast, sweeping paths follow the laws of gravity with perfect reliability. There are no sudden stops, no unexpected changes in direction. The planets simply continue their ancient dance, following paths that were established billions of years ago. This cosmic choreography creates a sense of order and predictability that spans the entire solar system, a gentle reminder that the universe operates according to dependable physical principles. The planets formed from a rotating disk of gas and dust about 4.5 billion years ago. As material condensed and gathered, it inherited the disk's rotation, causing planets to orbit in the same direction and roughly the same plane. This shared origin explains the orderly arrangement we observe today. The inner planets orbit relatively close to the Sun, completing their circuits in weeks or months. The outer planets orbit much farther out, taking years or decades to complete single revolutions. Mercury, the innermost planet, races around the Sun in just 88 Earth days. Venus takes 225 days. Earth, as you know, requires 365.25 days, which is why we add a leap day every 4 years to keep our calendars aligned. Mars needs 687 days to complete its orbit. These inner planets move quickly, responding to the Sun's strong gravitational pull at close range. The outer planets move more slowly through their vast orbits. Jupiter, the giant of the solar system, takes nearly 12 years to circle the Sun once. Saturn requires about 29.5 years. Uranus needs 84 years, and distant Neptune takes 165 years to complete a single orbit. Neptune has completed only one full orbit since its discovery in 1846. These long orbital periods reflect the enormous distances these planets travel, and the weaker gravitational pull they experience at such remote locations. The orbits are not perfect circles but slightly elliptical, meaning planets move a bit closer and farther from the Sun during each orbit. Earth's orbit is nearly circular, keeping seasonal temperature variations moderate. Mars has a more elliptical orbit, contributing to more extreme seasonal differences. Despite these variations, the orbits remain stable and predictable. Gravitational interactions between planets cause tiny perturbations, but these are small and well understood. Scientists can calculate planetary positions centuries into the past or future with remarkable accuracy. This orbital precision creates reliable patterns. Eclipses can be predicted years in advance because we know exactly where the Moon and Earth will be. Planetary alignments, though they have no physical significance, can be calculated long before they occur. Space missions rely on this predictability, launching spacecraft to arrive at distant planets years after launch, confident that both spacecraft and planet will meet at the appointed time and place. There's something deeply reassuring about this cosmic clockwork. The same laws of physics that governed planetary motion billions of years ago still govern it today, and will continue to govern it billions of years into the future. The planets won't suddenly veer off course. They won't collide or disappear. They'll simply continue their patient circuits around the Sun, maintaining the stable configuration that has existed since the solar system formed. This stability allowed life to emerge and evolve on Earth without catastrophic disruptions from planetary wanderings. It provides the consistent conditions necessary for complex systems to develop over billions of years. The orderly solar system, with its predictable rhythms and reliable patterns, creates a safe cosmic home where life can flourish and consciousness can emerge to contemplate the very laws that made it possible. And so the planets continue their ancient dance, following invisible curves through space, marking time with their movements, creating a cosmic symphony of mathematical precision and gentle, enduring stability. Light travels through the vacuum of space at about 186,000 miles per second, yet this journey is utterly silent. There's no sound in space, no rushing wind or roaring engines. Photons, the particles of light, simply glide through the darkness, carrying energy from stars to planets, from galaxies to telescopes, from the distant past to the present moment. When a photon leaves the surface of the Sun, it takes about 8 minutes to reach Earth, crossing 93 million miles of empty space in perfect silence. These particles of light require nothing to sustain them. They don't tire. They don't slow down unless they encounter matter, and they continue their journey for as long as the universe allows. This quiet persistence of light is one of the cosmos's most peaceful qualities. Photons are remarkable in their simplicity. They have no mass, no electric charge, just pure energy moving through space at the universe's speed limit. Once created, a photon continues in a straight line until something interrupts its path. It might travel for a fraction of a second before striking a nearby object, or it might journey for billions of years across intergalactic space, undisturbed and unchanged, until finally encountering a telescope mirror or a distant planet. The silence of this journey is absolute. Sound requires a medium to travel through, molecules of air or water that can vibrate and carry pressure waves. In the vacuum of space, there are no molecules to vibrate, no medium to conduct sound. Even the most energetic events, supernova that release more energy in seconds than our Sun will produce in its entire lifetime, occur in complete silence. The light from these events propagates outward, but no sound accompanies it. Space is the quietest environment in the universe. When you see sunlight streaming through a window, you're witnessing the end of an 8-minute journey that began deep within the sun's core. Actually, the story begins much earlier. The photon's energy was created through nuclear fusion at the sun's center, but that energy took thousands of years to work its way outward through the dense solar interior, absorbed and re-emitted countless times by hot plasma. Only when it finally reached the sun's surface did it begin its swift, unimpeded journey through empty space toward Earth. These photons carry the warmth that makes Earth habitable. They carry the light that plants use for photosynthesis. They carry the ultraviolet radiation that created Earth's ozone layer. They carry the visible light that allows you to see the world around you. All of this energy, all of this information, travels silently across the void, requiring nothing but empty space to complete its journey. Light from distant stars has travelled much farther. The photons reaching your eyes from stars hundreds or thousands of light years away have been journeying through space longer than human civilization has existed. They've crossed vast distances where matter is extraordinarily sparse, perhaps encountering only a few atoms of hydrogen in a space the size of a room. These occasional encounters might scatter the photon slightly, changing its direction by a tiny amount, but otherwise the journey continues unimpeded. Photons from distant galaxies have travelled for billions of years. The most distant objects we can observe emitted their light when the universe was young, less than 1 billion years old. Those photons have been travelling through expanding space for over 13 billion years, gradually losing energy as the wavelength stretches, but never stopping, never deviating from their straight-line path. They've crossed distances so vast that expressing them in miles becomes meaningless. We measure these distances in billions of light years, and still the photons persist, silent and patient, carrying their ancient message across the cosmos. There's something deeply peaceful about this image. Throughout the universe, countless photons are travelling through the darkness, each following its own straight path, none interfering with the others, all moving in perfect silence. The universe is filled with light, yet the journey of each individual photon is solitary and quiet. This light requires no effort to maintain. It asks nothing from the universe. It simply continues, constant and eternal, until its journey ends. And so light fills the cosmos, streaming from every star, reflecting from every planet, carrying information and energy across the silent depths of space, connecting distant worlds through invisible threads of electromagnetic radiation. Between the stars lies vast emptiness, regions where matter is so sparse that a single hydrogen atom might occupy several cubic centimeters of space. This interstellar medium is neither cold nor hot in the way we experience temperature. It simply exists in a state of calm equilibrium. There's no weather in interstellar space, no storms or turbulence, just gentle stillness extending across light years. Occasionally clouds of gas and dust drift through these regions, but even these clouds move slowly, patiently, taking millions of years to traverse the distances between stars. This peaceful emptiness isn't desolate or lonely. It's simply quiet, a cosmic rest area where matter waits patiently for gravity to gather it into new stars and planets. In these vast spaces between stars, the universe breathes slowly, taking its time between one creation and the next. The distances between stars are difficult to comprehend. The nearest star to our Sun, Proxima Centauri, lies about 4 light-years away. That's approximately 25 trillion miles. In all that space between our Sun and Proxima Centauri, there are no planets, no asteroids, no substantial objects, just hydrogen and helium atoms drifting in the darkness, spread so thinly that each atom might be separated from its nearest neighbour by several inches or more. This extreme sparseness creates an environment unlike anything we experience on Earth. On our planet, matter is dense. Air contains trillions of molecules in every cubic inch. Even the best vacuum we can create in laboratories contains millions of particles per cubic inch. But in the interstellar medium, densities are billions of times lower. In some regions, you might find only 1 atom per cubic centimetre. In others, particularly in the voids between spiral arms, density drops even further. Temperature in interstellar space is an unusual concept. With so few particles, there's nothing to feel hot or cold in the traditional sense. Individual atoms might have high energies, meaning they're moving quickly, but with so few of them, they can't transfer heat effectively. A thermometer placed in interstellar space would register temperatures based on radiation, not particle collisions. It would cool down to a few degrees above absolute zero, radiating away its heat into the darkness, receiving only the faint warmth of starlight and the cosmic microwave background. Despite this apparent emptiness, the interstellar medium isn't completely uniform. Clouds of gas and dust drift through these regions, denser accumulations where atoms have gathered. These clouds are still extraordinarily sparse by Earth standards, but they're dense enough to eventually collapse under their own gravity and form new stars. The clouds move slowly, carried by gravitational influences from nearby stars and by pressure from stellar radiation. A typical cloud might drift at a few miles per second, which seems fast until you consider the distances involved. At such speeds, crossing a single light-year takes thousands of years. The interstellar medium plays important roles in the galaxy's ecology. It provides the raw material for new stars and planets. It absorbs and redistributes energy from dying stars. It carries magnetic fields that thread through the galaxy. It serves as a medium through which cosmic rays travel. Yet despite this activity, the overall impression is one of peace and stillness. Changes happen slowly. Interactions are gentle. Nothing rushes or hurries in the vast spaces between stars. There's beauty in this emptiness. It's a kind of cosmic silence, a pause between notes in the universe's long composition. Stars are the active elements, the sources of light and energy. But between them lie these quiet regions where matter rests, where photons travel undisturbed, where the universe simply exists without drama or urgency. You don't need to hold on to these thoughts. Just let them drift through your mind gently, like atoms drifting through the interstellar medium. This peaceful emptiness will persist for billions of years, providing the space through which light travels, the canvas upon which cosmic structures paint themselves, the silent backdrop against which the drama of stellar life plays out. It asks nothing, offers no resistance, simply continues its quiet existence across the galaxy. Stars don't burst into existence suddenly. They form gradually within vast clouds of gas and dust called nebulae, regions where matter slowly gathers under gravity's gentle pull. Over hundreds of thousands of years, these clouds compress, growing denser and warmer at their centers. Eventually, when the pressure and temperature become high enough, nuclear fusion begins and a star ignites. But even this ignition isn't an explosion. It's a gradual brightening, a steady increase in light and warmth as the star settles into its long, stable existence. The process is patient and unhurried, following the same pattern that has created billions of stars throughout the galaxy. Within the Orion Nebula, about 1,300 light-years away, new stars are forming right now, continuing this ancient cycle that has been unfolding for billions of years. The process begins when a region within a nebula becomes slightly denser than its surroundings. Perhaps a shock wave from a nearby supernova passed through, compressing the gas. Perhaps random motions caused matter to accumulate. Whatever the cause, once a region becomes denser, its gravity increases slightly, pulling in more material from the surrounding cloud. This creates a positive feedback loop. More mass means stronger gravity, which attracts more mass, which strengthens gravity further. As the cloud contracts, it begins to rotate faster, conserving angular momentum like a figure skater pulling in their arms during a spin. The rotation causes the cloud to flatten into a disk, with most of the mass concentrated at the center. This central concentration will become the star. The surrounding disk may eventually form planets. The process takes time, typically a few 100,000 years from initial collapse to the birth of a star. During this contraction, gravitational potential energy converts to heat. The cloud's center grows warmer as it compresses. At first, the heat escapes easily, radiated away as infrared light. But as the cloud grows denser, it becomes harder for heat to escape. The temperature rises. When the central temperature reaches about 10 million degrees Celsius, hydrogen nuclei begin to fuse together, forming helium and releasing energy. This is the moment of stellar birth, when nuclear fusion begins and the star turns on. But this turning on isn't sudden. The fusion rate increases gradually as the temperature rises. The star slowly brightens over thousands of years, settling into a stable configuration where gravity pulling inward perfectly balances the outward pressure from heat and radiation. Once this balance is achieved, the star enters its main sequence phase, where it will remain stable for millions or billions of years, depending on its mass. The Orion Nebula provides a beautiful example of ongoing star formation. Located in the Sword of Orion, visible as a fuzzy patch to the naked eye, this nebula spans about 24 light-years across. Within its glowing clouds, hundreds of young stars have already formed, and more are condensing from the nebula's dense regions. Some of these protostars are still hidden within thick cocoons of dust, detectable only in infrared light. Others have emerged, their brilliant light illuminating the surrounding gas and creating the nebula's characteristic glow. The Orion Nebula is relatively close to Earth, about 1,300 light-years away, making it one of the best-studied star-forming regions. Observations reveal stars at various stages of formation, from dense cores just beginning to collapse to young stars only a few 100,000 years old, still surrounded by their planetary disks. This allows astronomers to study the entire process of star formation in a single region. Star formation is one of the universe's fundamental processes. Every star in the night sky formed this way, through the patient gravitational collapse of interstellar clouds. Our Sun formed this way 4.5 billion years ago, probably within a cluster of other stars that have since drifted apart. The atoms in your body were forged in earlier generations of stars that formed, lived, and died before the Sun was born. And throughout the galaxy, the process continues. New stars condensing from nebulae, carrying on the cycle of stellar birth and death that has shaped the cosmos since the first stars formed over 13 billion years ago. Our Sun has been shining steadily for about 4.5 billion years, and it will continue to do so for roughly another 5 billion years. This extraordinary stability is the result of a delicate balance between gravity pulling inward and the pressure from nuclear fusion pushing outward. Every second, the Sun converts about 600 million tons of hydrogen into helium, releasing energy that warms Earth and sustains life. This process happens with such consistency that the Sun's output varies by less than 0.1% over decades. You can count on the Sun to rise each morning, to provide warmth and light throughout the day, and to set each evening in a pattern that has repeated since long before human beings walked the Earth. This stellar constancy is one of the most reassuring facts about our place in the cosmos. The Sun is a middle-aged star, about halfway through its stable lifespan. It's neither young nor old, neither exceptionally large nor small. Its mass is about 2 × 10⁻³ kilograms, containing about 99.86% of all the mass in the solar system. Despite this enormous mass, the Sun's density is relatively modest, only about 1.4 times that of water. It's composed mostly of hydrogen, about 73% by mass, with helium making up about 25%, and heavier elements comprising the remaining 2%. At the Sun's core, where temperatures reach about 15 million degrees Celsius and pressures are enormous, hydrogen nuclei overcome their electrical repulsion and fuse together through a process called the proton-proton chain. 4 hydrogen nuclei eventually combine to form one helium nucleus, releasing energy in the form of gamma-ray photons and neutrinos. The energy released by this fusion creates the outward pressure that balances gravity's inward pull. This balance is extraordinarily precise. If fusion produced slightly less energy, the Sun would contract, increasing the core temperature and speeding up fusion until balance was restored. If fusion produced too much energy, the Sun would expand, cooling the core and slowing fusion until equilibrium returned. This self-regulating mechanism, called hydrostatic equilibrium, keeps the sun stable over billions of years. Small variations occur, but the overall output remains remarkably constant. The energy generated at the core takes a long time to reach the surface. Photons are absorbed and re-emitted countless times as they work their way through the dense solar interior. A photon created by fusion in the core might take 100,000 years or more to reach the surface, bouncing randomly through the layers of the sun. But once it reaches the surface, it escapes into space and travels to Earth in just 8 minutes. This steady energy output makes life possible on Earth. Plants rely on consistent sunlight for photosynthesis. Ocean currents and weather patterns depend on solar heating. The water cycle operates because sunlight evaporates water from oceans and lakes. Earth's entire climate system is tuned to the sun's current output. If the sun's brightness varied significantly, Earth's climate would become unstable, making complex life difficult or impossible. The sun has been this stable for billions of years. When the first simple cells emerged on Earth nearly 4 billion years ago, the sun was shining, perhaps slightly less brightly than today, but steadily and reliably. Throughout the entire history of life on Earth, through the evolution of photosynthesis, the emergence of complex cells, the rise of multicellular organisms, the colonization of land, the age of dinosaurs, and the evolution of humans, the sun has continued its patient fusion, providing the energy that powers the biosphere. Looking ahead, the sun will continue this stable existence for roughly another 5 billion years. Eventually, it will exhaust the hydrogen in its core and begin burning hydrogen in a shell around the core. This will cause the sun to expand into a red giant, but that transformation lies in the distant future. For now and for billions of years to come, the sun will continue its reliable operation, rising and setting with perfect regularity, warming the planet, driving the seasons, maintaining the patterns of day and night that have structured life on Earth since its beginning. Filling all of space is a faint, gentle glow called the cosmic microwave background radiation. This ancient light dates back nearly 14 billion years to when the universe first became transparent. Though invisible to your eyes, this radiation bathes everything in a uniform warmth of about 3 degrees above absolute zero. This persistent glow represents the universe's earliest light, cooled and stretched by billions of years of cosmic expansion. It's remarkably uniform across the entire sky, varying by only tiny fractions of a degree from one region to another. This uniformity reveals that the universe began in a state of relative smoothness, without dramatic variations or turbulence. The cosmic background radiation is like a gentle hum permeating all existence, a quiet reminder of the universe's ancient origins and its remarkably peaceful beginning. This radiation was discovered by accident in 1965 by Arno Penzias and Robert Wilson, 2 radio astronomers working at Bell Laboratories. They were trying to eliminate background noise from their antenna and found a persistent signal coming from all directions in the sky. No matter where they pointed their instrument, the signal remained uniform and unchanging. After eliminating all possible terrestrial sources, they realized they had detected the afterglow of the Big Bang, a prediction made by cosmologists but never before observed. The cosmic microwave background originated about 380,000 years after the Big Bang. Before this time, the universe was filled with hot plasma, a soup of electrons and atomic nuclei too energetic to form stable atoms. Photons constantly scattered off these free electrons, making the universe opaque, like being inside a thick fog. But as the universe expanded and cooled, it eventually reached a temperature where electrons could combine with nuclei to form neutral atoms, primarily hydrogen and helium. This process, called recombination, made the universe transparent. Photons could suddenly travel freely, no longer scattered by free electrons. These photons have been travelling through space ever since. When these photons were released, they had a temperature of about 3,000 degrees Celsius, glowing in visible and near-infrared light. But the universe has expanded enormously since then, stretching the wavelengths of these photons by a factor of about 1,000. This stretching, called cosmological redshift, has cooled the radiation down to its current temperature of about 2.7 degrees above absolute zero, or negative 270 degrees Celsius. The photons that were once visible light are now microwaves, invisible to the human eye but detectable by radio telescopes. The uniformity of this radiation is remarkable. Across the entire sky, the temperature varies by less than 1 part in 100,000. This indicates that the early universe was extraordinarily smooth and uniform. However, there are tiny variations, small regions that are slightly warmer or cooler than average. These fluctuations represent slight differences in density in the early universe. Regions that were slightly denser had slightly stronger gravity, eventually pulling in more matter to form galaxies and clusters. The patterns in the cosmic microwave background are essentially the seeds from which all cosmic structures grew. Studying this radiation provides a window into the universe's infancy. The patterns of temperature fluctuations encode information about the universe's composition, age, geometry, and history. Measurements from satellites like COBE, WMAP, and Planck have mapped these fluctuations with exquisite precision, allowing cosmologists to determine that the universe is about 13.8 billion years old, that it's geometrically flat, and that it contains roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. The cosmic microwave background surrounds you constantly, right now as you rest. This ancient light is passing through your body, a gentle rain of photons that have been travelling for nearly 14 billion years. These photons began their journey when the universe was young and hot, and they'll continue travelling until they encounter matter, or are red-shifted to even longer wavelengths by the universe's continued expansion. This radiation connects you directly to the universe's earliest moments, a tangible relic from cosmic dawn, a peaceful glow that fills all of space and time. Galaxies like our Milky Way form beautiful spiral patterns, with arms of stars, gas, and dust sweeping gracefully outward from a central bulge. These spiral arms aren't rigid structures, they're density waves, regions where stars and gas naturally congregate as they orbit the galactic center. As material moves through these arms, it compresses slightly, triggering the formation of new stars that illuminate the spiral pattern. The process happens slowly, over millions of years, creating the elegant shapes we observe. Our solar system orbits the galactic center once every 250 million years, drifting through these spiral arms like a leaf floating on a gentle stream. The pattern is predictable, following the laws of gravity and motion, creating a sense of cosmic order that extends across hundreds of thousands of light years. Think of a spiral galaxy as a vast cosmic pinwheel, slowly rotating in space. The Milky Way, our home galaxy, spans about 100,000 light-years across and contains between 200 and 400 billion stars. These stars orbit the galactic center at different speeds depending on their distance, creating a differential rotation that gives rise to the spiral pattern. Stars closer to the center orbit faster than those farther out, and this difference in orbital speeds generates waves of compression that sweep through the galactic disk. These density waves are similar to traffic jams on a highway. Cars enter a congested region, slow down, then speed up again as they exit. The jam itself moves more slowly than the individual cars. In the same way, stars and gas clouds enter a spiral arm, slow down slightly as they pass through the denser region, then speed up again as they exit. The spiral arm moves through the galaxy at its own pace, separate from the motion of individual stars. Within the spiral arms, the increased density of gas triggers star formation. As gas clouds drift into the denser regions, they compress slightly, and this compression can be enough to initiate gravitational collapse. New stars form, particularly massive bright blue stars that live only a few million years. These luminous young stars make the spiral arms visible, outlining the pattern with their brilliant light. By the time these stars die, they've moved out of the spiral arm, and new stars have formed within it to take their place. Our solar system currently resides between two major spiral arms of the Milky Way, in a smaller feature called the Orion Spur or Local Arm. We're located about 26,000 light-years from the galactic center, orbiting at a speed of about 500,000 miles per hour. Despite this tremendous velocity, our orbital period is so long that the Sun has completed only about 20 orbits, since it formed 4.5 billion years ago. During Earth's history, dinosaurs lived and died, continents drifted across the planet's surface, and life evolved from simple cells to complex organisms, all while the solar system completed less than one trip around the galaxy. The spiral pattern itself rotates more slowly than the stars. It takes several 100 million years for the pattern to complete one rotation. This means stars drift in and out of spiral arms as they orbit. The solar system likely passes through a spiral arm every few tens of millions of years. Some scientists have speculated that these passages might influence Earth's climate or impact rates, but the effects, if they exist at all, are subtle and difficult to detect in the geological record. Other spiral galaxies throughout the universe display similar patterns. The Andromeda Galaxy, our nearest large galactic neighbour about 2.5 million light-years away, shows a beautiful spiral structure visible even through small telescopes. The Whirlpool Galaxy, about 23 million light-years distant, presents a face-on view that reveals the elegant symmetry of its spiral arms. Each galaxy creates its pattern through the same basic physics, gravity, and rotation, combining to generate these graceful cosmic structures. The spiral arms will persist for billions of years, maintained by the continuous differential rotation of the galaxy. Stars will continue their patient orbits, passing through the arms periodically, following paths that have been set by the galaxy's gravitational field. The pattern provides structure and order to the galactic disk, organizing star formation and creating the beautiful shapes we observe across the universe. Many stars in the galaxy don't exist alone. About half of all stars belong to binary or multiple star systems, where two or more stars orbit around a common center of mass. These orbital dances can last for years, centuries, or even millions of years, depending on the stars' distances from each other. The stars circle one another with clockwork precision, their paths determined by gravity and momentum. Some binary systems are so close that they complete an orbit in just a few days. Others are separated by such vast distances that their orbital periods stretch across thousands of years. Regardless of the timescale, these stellar partnerships demonstrate the universe's tendency towards stable, long-lasting relationships. Binary stars have been orbiting each other since they formed, and they'll continue their patient dance for billions of years to come. Binary stars form when a collapsing gas cloud fragments into two or more dense cores instead of forming a single star. Each core continues to contract and eventually ignites fusion, but the two stars remain gravitationally bound, orbiting their common center of mass. This center of mass, called the barycenter, lies somewhere between the two stars, closer to the more massive one. Both stars orbit around this point, maintaining a perfect balance. The closest binary systems have orbital periods measured in hours or days. These stars are so near each other that their outer atmospheres may actually touch, exchanging material in a complex interaction. Despite this proximity, the orbits remain stable, with each star maintaining its identity. Slightly wider binaries have orbital periods of weeks or months. These systems are common and have been studied extensively, allowing astronomers to determine stellar masses with high precision by measuring the orbital speeds and periods. At the other extreme, some binary stars are separated by thousands of astronomical units, taking thousands or even tens of thousands of years to complete a single orbit. These wide binaries appear as separate stars to the casual observer, but sensitive measurements reveal their slow mutual orbit. The gravitational bond between such distant companions is weak, and passing stars might occasionally disrupt the system, but most survive for billions of years, slowly circling each other in the darkness. Binary stars offer unique laboratories for studying stellar physics. By observing how stars orbit each other, astronomers can calculate their masses directly, something that's difficult or impossible for single stars. The orbital period and separation provide all the information needed to determine the combined mass of the system using Newton's laws of motion and gravity. If astronomers can also determine the individual orbital motions of each star around the barycenter, they can calculate each star's mass separately. Some binary systems produce eclipses, when one star passes in front of the other from our perspective. The total light we receive temporarily decreases. These eclipsing binaries provide additional information about stellar sizes and shapes. The duration and depth of the eclipses reveal how large the stars are and how their brightness varies across their surfaces. Such systems have been studied for over a century, contributing enormously to our understanding of stellar structure and evolution. Binary stars can also affect each other's evolution. If one star is significantly more massive than its companion, it will evolve faster, eventually expanding into a red giant. If the companion is close enough, the expanding star may transfer material to it, rejuvenating the companion and altering both stars' evolutionary paths. These interactions can lead to exotic objects like white dwarf binaries, neutron star binaries, or even black hole binaries. Despite these occasional interactions, most binary systems evolve peacefully, with each star following its own life cycle while maintaining its orbital relationship with its companion. The stars age together, having formed at the same time from the same molecular cloud. They share a common history, a cosmic partnership that began billions of years ago and will continue until one or both stars reach the end of their lives. There's something beautiful about this companionship. Two stars bound together by gravity, circling endlessly through space, stable and constant over timescales that dwarf human comprehension. When a star like our Sun reaches the end of its life, it doesn't explode violently. Instead, it gently releases its outer layers into space, creating a glowing shell of gas called a planetary nebula. These structures aren't planets at all. They're the beautiful remnants of stars illuminated by the hot core left behind. Planetary nebulae come in various shapes and colours, each one unique, glowing softly in shades of red, green, and blue, as different elements emit light at specific wavelengths. These nebulae expand slowly outward, gradually dispersing into the interstellar medium over thousands of years. They represent a peaceful ending to a star's life cycle, a gentle return of material to the cosmos from which new stars and planets can eventually form. The Ring Nebula, about 2,000 light-years away, is one such example, a cosmic reminder that even stellar death can be beautiful and calm. The formation of a planetary nebula begins when a sun-like star exhausts the hydrogen fuel in its core. Without fusion to provide outward pressure, the core contracts under gravity, heating up until it's hot enough to fuse helium into carbon and oxygen. Meanwhile, hydrogen fusion continues in a shell around the contracting core. This shell fusion produces so much energy that the star's outer layers expand enormously, transforming the star into a red giant hundreds of times its original size. During this red giant phase, which lasts several 100 million years, the star loses mass gradually through stellar winds. The outer layers, only loosely bound to the star, drift outward into space, driven by radiation pressure and pulsations in the star's atmosphere. Eventually, the star sheds enough mass that the hot core becomes exposed, no longer hidden beneath layers of cooler gas. This exposed core, though small, is extraordinarily hot. with surface temperatures reaching 50,000 to 100,000 degrees Celsius. The intense ultraviolet radiation from this hot core ionizes the previously ejected gas, causing it to glow. Different elements emit light at different wavelengths, creating the characteristic colours of planetary nebulae. Hydrogen emits red light, oxygen produces green and blue light, and nitrogen adds additional red hues. The combination creates the beautiful, colourful structures we observe. The shapes of planetary nebulae vary widely. Some are roughly spherical, others are elliptical, and some show complex bipolar structures with lobes extending in opposite directions. The Ring Nebula is approximately ring-shaped, or more accurately cylindrical, appearing as a ring because we're viewing it at an angle. The Helix Nebula, closer at about 650 light-years, resembles a cosmic eye. The Butterfly Nebula displays dramatic bipolar lobes. Each shape reflects the particular circumstances of the star's death, including its rotation, magnetic fields, and whether it had a binary companion. These nebulae expand at speeds of about 10 to 20 miles per second, which seems fast but means they grow slowly on human timescales. A typical planetary nebula expands by about 1 light-year over 10,000 years. As they expand, they fade gradually, their gas spreading and thinning until it merges with the interstellar medium. Most planetary nebulae remain visible for only 10,000 to 20,000 years before dispersing completely. The hot core left behind gradually cools, becoming a white dwarf, the final stage for stars like our Sun. This white dwarf contains about half the original star's mass compressed into a volume about the size of Earth. It no longer generates energy through fusion, but simply radiates away its stored heat over billions of years. The white dwarf will remain, cooling slowly, long after the planetary nebula has dispersed and vanished. Planetary nebulae return enriched material to the galaxy. The dying star has converted some of its hydrogen and helium into heavier elements like carbon, nitrogen and oxygen through nuclear fusion. These elements, essential for planets and life, now drift through space, eventually incorporating into new clouds that will form new stars and planetary systems. In this way, stellar death contributes to cosmic evolution, enriching the galaxy with the chemical elements necessary for complexity and life. Allow yourself to simply listen and drift as we continue this gentle journey through the cosmos. The constellations you see in the night sky appear fixed and unchanging throughout a human lifetime, but they're actually moving slowly through space. Each star in a constellation has its own motion, drifting gradually in its orbit around the galactic center. Over thousands of years, these movements will change the shapes of constellations, but the change happens so slowly that many generations will pass before it becomes noticeable. This glacial pace of stellar motion provides a sense of cosmic permanence. The Big Dipper has looked roughly the same for thousands of years, serving as a familiar guide to countless generations of stargazers. The stars will continue their patient drift through the galaxy, eventually creating new patterns in the sky, but never hurrying, never rushing, simply following their predetermined path through space at their own steady pace. Constellations are human constructs, patterns we've imposed on the random distribution of stars as seen from Earth. These stars in any given constellation are usually at very different distances from us and have no physical connection to each other. They simply happen to lie in roughly the same direction as viewed from our solar system. The 7 bright stars forming the Big Dipper, for example, range in distance from about 80 light-years to over 120 light-years from Earth. Each of these stars moves through space with its own velocity, determined by its initial formation conditions and subsequent gravitational interactions. Some stars are moving toward us, others away. Some are moving perpendicular to our line of sight. This motion, called proper motion, gradually shifts each star's position on the sky. For most stars, the proper motion is tiny, measured in fractions of an arcsecond per year. An arcsecond is 1/3600th of a degree, so these motions are imperceptible to the unaided eye over human timescales. But given enough time, these small motions add up. 50,000 years ago, the Big Dipper looked noticeably different. The 2 stars at the ends of the Dipper's bowl were in different positions relative to the others, giving the pattern a somewhat altered shape. 50,000 years from now, the configuration will have changed again, with some stars having moved closer together and others farther apart. Eventually, in a few 100,000 years, the Big Dipper will be unrecognizable. Other constellations show similar slow evolution. Orion, one of the most recognizable patterns in the sky, will maintain its current shape for tens of thousands of years, but eventually the stars will drift and the hunter's form will blur and change. The stars forming Orion's belt, 3 bright stars in a nearly straight line, are moving in slightly different directions and will eventually break their alignment. Despite these changes, the night sky provides a sense of continuity across human history. The constellations visible to ancient astronomers thousands of years ago are essentially the same ones we see today. The patterns guided ancient navigators, marked the seasons for early farmers, and inspired mythologies across cultures. When you look at the Big Dipper or Orion, you're seeing patterns that countless humans throughout history have also seen, connecting you to a shared experience that spans civilizations and millennia. This slow stellar drift is part of the galactic dance. All stars orbit the galactic center, each following its own path determined by the overall gravitational field of the Milky Way. Stars closer to the galactic center orbit faster than those farther out. Stars in different parts of the galaxy move in different directions. These differential motions gradually rearrange the stellar neighborhood over millions of years. Our Sun, along with its neighboring stars, participates in this motion, moving through space at about 500,000 miles per hour relative to the galactic center. The nearby stars move at similar speeds but in slightly different directions, causing their positions relative to each other to shift gradually. Over the Sun's lifetime, it has encountered thousands of different stellar neighbors as both the Sun and other stars follow their orbital paths through the galaxy. The stars will continue this patient drift for billions of years. They won't hurry, they won't rush. They simply follow the gravitational contours of the galaxy, tracing out their predetermined paths through space and time. And in the distant future, long after human civilization has faded, the stars will have rearranged themselves into new patterns, creating constellations that no human will ever name or recognize, but which will be just as beautiful, just as peaceful as the patterns we see tonight. The average distance between stars in our galaxy is about 4 light years, though this varies depending on location. In the spiral arms, stars are packed more closely. In the spaces between arms, they are more spread out. This vast emptiness might seem lonely, but it's actually beneficial for planetary systems. The large distances mean that stars rarely pass close enough to each other to disrupt planetary orbits. The Sun's nearest stellar neighbours, the 3 stars of the Alpha Centauri system, pose no threat to Earth or any other planet in our solar system. They're simply too far away to exert significant gravitational influence. This cosmic spacing allows solar systems to evolve undisturbed for billions of years, giving life the time and stability it needs to emerge and flourish. The emptiness between stars is protective, a peaceful buffer that ensures each star system can develop according to its own quiet rhythm. In denser regions of the galaxy, particularly in globular clusters or the galactic core, stars are packed much more tightly. In these regions, the average distance between stars might be less than 1 light year, or even a few trillion miles. If Earth were located in such a region, the night sky would be spectacular, filled with thousands of bright stars. But the close spacing would also pose risks. Passing stars could disturb the orbits of comets in the outer solar system, potentially sending them toward the inner planets. In the galactic disk where we reside, the spacing is much more generous. The nearest star system to our Sun, Alpha Centauri, lies about 4.2 light years away, or roughly 25 trillion miles. This is a typical separation for stars in our neighborhood. To grasp this scale, imagine the Sun reduced to the size of a basketball. On this scale, Earth would be about 80 feet away, smaller than a grain of rice. The nearest star would be about 4,000 miles away, roughly the distance from New York to Los Angeles. This gives you a sense of how empty space really is between stars. This vast emptiness provides stability. Gravitational interactions between stars become negligible at such distances. A star 4 light-years away exerts almost no gravitational pull on objects in our solar system. Even the massive planets in the outer solar system feel only the Sun's gravity, not the influence of neighbouring stars. This isolation allows planetary orbits to remain stable over billions of years. Occasionally, a star does pass relatively close to the solar system. About every few million years, a star might pass within 1 or 2 light years of the Sun. Even these close passages rarely cause significant disruptions. The gravitational influence is weak at such distances. Though it might perturb objects in the Oort cloud, a distant shell of comets that surrounds the solar system at distances of thousands of astronomical units. Some of these perturbed comets might be nudged onto paths that bring them into the inner solar system, but these events are infrequent and don't threaten planetary stability. The spacing between stars also means that stellar collisions are extraordinarily rare. Even in globular clusters where stars are packed relatively tightly, direct collisions occur only once every few million years. In the galactic disk, such events are virtually unheard of. Stars are so small compared to the distances between them that even when entire galaxies merge, individual stellar collisions are extremely unlikely. The stars simply pass by each other, their gravitational interactions reshaping the overall structure, but rarely bringing two stars into direct contact. This protective spacing has allowed our solar system to evolve peacefully for 4.5 billion years. The planets have maintained stable orbits. Earth has remained in the habitable zone where liquid water can exist. Life has had time to emerge, evolve, and develop complexity. All of this was possible because our stellar neighborhood is spacious and quiet, free from disruptive close encounters. Looking ahead, this situation will continue for billions of years. The Sun will remain isolated, surrounded by its protective buffer of empty space. The nearest stars will continue their slow drift, maintaining safe distances. The solar system will continue its peaceful orbit around the galactic center, undisturbed by stellar traffic. And in this quiet corner of the galaxy, life on Earth can continue its long evolutionary journey, sheltered by the vast, peaceful void between the stars. Galaxies, galaxy clusters, and the cosmic web all formed gradually over billions of years. Small fluctuations in the density of matter in the early universe served as seeds, and gravity amplified these tiny variations over time. Matter slowly accumulated in regions that were slightly denser, forming the first stars and galaxies within a few 100 million years after the Big Bang. Over billions of years, these structures continued to grow and evolve, galaxies merging, clusters forming, and vast filaments of matter stretching across hundreds of millions of light years. This process continues today, though at a slower pace than in the universe's youth. The evolution happens gradually, without sudden disruptions, following the patient pull of gravity. Each structure builds upon what came before, creating the intricate cosmic architecture we observe across the universe. The story of cosmic structure begins in the first moments after the Big Bang. The early universe was remarkably smooth, but not perfectly so. Tiny fluctuations in density, variations of only 1 part in 100,000, existed in the primordial plasma. These minute differences were imprinted during the first fraction of a second of cosmic history, likely by quantum fluctuations stretched to cosmic scales during a period of rapid expansion called inflation. As the universe expanded and cooled, these density variations had profound consequences. Regions that were slightly denser had slightly stronger gravity. This stronger gravity attracted more matter from surrounding regions, making these areas even denser. Regions that were slightly less dense lost matter to their denser neighbours, becoming even emptier. This process, driven entirely by gravity, gradually amplified the initial tiny fluctuations into substantial differences in density. Within a few 100 million years after the Big Bang, the densest regions had accumulated enough matter to form the first stars and small galaxies. These early galaxies were much smaller than the Milky Way, typically containing millions rather than billions of stars. They appeared in regions where the primordial density fluctuations had been strongest, marking the locations of future galaxy clusters and filaments. Over the next several billion years, these small galaxies merged and grew. When two galaxies drifted close together, their mutual gravity pulled them into increasingly tight orbits. Eventually, they merged, combining their stars, gas, and dark matter into a single larger galaxy. This process built up the massive galaxies we see today, including our own Milky Way, which likely formed through the merger of numerous smaller galaxies over billions of years. Meanwhile, on larger scales, gravity organized matter into a cosmic web. Galaxies clustered along vast filaments of dark matter, creating dense nodes where thousands of galaxies gathered. Between these filaments, vast voids appeared, regions with very few galaxies where matter had been pulled away toward denser areas. This web-like structure stretches across hundreds of millions of light years, creating the large-scale architecture of the universe. The cosmic web continues to evolve today. Galaxies still merge, though less frequently than in the universe's youth. Clusters continue to grow as smaller groups fall into them. Filaments gradually become more defined as matter flows along them. The voids slowly expand as the universe itself expands. But all these changes happen gradually, following predictable patterns determined by gravity and the initial distribution of matter. Computer simulations can recreate this cosmic evolution. Starting from the density fluctuations observed in the cosmic microwave background, simulations let gravity act on dark matter and ordinary matter for billions of simulated years. The results match remarkably well with observations of the actual universe, producing cosmic webs, galaxy clusters, and void distributions that closely resemble what telescopes reveal. This agreement gives astronomers confidence that they understand the fundamental processes shaping cosmic structure. The gradual nature of this evolution is one of its most striking features. There are no sudden transformations, no abrupt reorganizations. Structures simply grow and merge according to gravity's patient pull. A galaxy cluster visible today has been assembling for billions of years, gradually pulling in smaller groups and individual galaxies. The process will continue for billions more years, with the cluster slowly growing larger and more massive. This evolutionary story connects the early universe's tiny fluctuations to the rich structures we observe today. The galaxy clusters, the cosmic filaments, even the position of the Milky Way within its local group of galaxies, all trace back to those minute density variations in the first moments after the Big Bang. Every cosmic structure carries a history stretching back to the universe's beginning, a history written in its position, its motion, and its relationships with neighboring structures. Planets orbit their stars in relatively circular paths, held in place by a delicate balance between gravity and momentum. This creates stable environments where conditions can remain consistent for billions of years. In our solar system, the planets have maintained their orbits with remarkable regularity since they formed about 4.5 billion years ago. The inner planets, Mercury, Venus, Earth, and Mars, circle the Sun relatively quickly. The outer planets, Jupiter, Saturn, Uranus, and Neptune, take much longer. This hierarchical structure is common in planetary systems throughout the galaxy. The orbits are predictable, following mathematical principles that allow us to calculate planetary positions far into the past and future. This orbital harmony is essential for the development of life, providing the stable conditions necessary for evolution to unfold over billions of years. Each planet maintains its orbit through a perfect balance. Gravity pulls the planet toward the Sun, while the planet's momentum carries it forward. These two effects combine to create a curved path around the Sun, neither falling inward nor flying outward, just continuously circling. This balance is self-maintaining. If a planet somehow moved slightly closer to the Sun, gravity would strengthen, speeding up the planet until it swung back outward. If it moved farther out, gravity would weaken, slowing the planet until it fell back inward. Small perturbations correct themselves naturally. The inner planets complete their orbits relatively quickly. Mercury, closest to the Sun, races around in just 88 days. Venus takes 225 days. Earth requires 365.25 days. Mars needs 687 days. These short orbital periods reflect both the smaller distances these planets travel and the stronger gravitational pull they experience near the Sun. The outer planets move much more slowly. Jupiter takes nearly 12 years to orbit the Sun once. Saturn needs about 29.5 years. Uranus requires 84 years. Neptune takes 165 years. These long periods result from the enormous distances these planets must traverse, and the weaker solar gravity at such remote locations. Neptune, for example, travels about 28 billion miles to complete one orbit. The orbits aren't perfect circles, but ellipses, with the Sun at one focus. However, most planetary orbits in our solar system are nearly circular, meaning the ellipses are only slightly elongated. Earth's orbit brings it about 91.5 million miles from the Sun at closest approach, and about 94.5 million miles at farthest distance, a variation of only about 3%. This near circularity helps maintain stable temperatures throughout the year. The planets all orbit in roughly the same plane, called the ecliptic, another consequence of their formation from a flattened disk of gas and dust. The largest deviation from this plane is Pluto, which orbits at a 17-degree angle, one reason it was reclassified as a dwarf planet. The major planets all stay within a few degrees of the ecliptic plane, creating an orderly, flattened structure. Gravitational interactions between planets cause small variations in their orbits over time. Jupiter, by far the most massive planet, exerts the strongest influence on its neighbours. Its gravity can slightly stretch or tilt the orbits of other planets over thousands or millions of years. However, these perturbations are small and predictable. The solar system's overall configuration remains stable, with no planets likely to have their orbits significantly disrupted over billions of years. This stability extends to planetary systems throughout the galaxy. Observations of exoplanets, planets orbiting other stars, reveal similar orbital arrangements. Many systems have planets in nearly circular orbits around their stars. Some systems show different architectures, with massive planets close to their stars or planets in highly elliptical orbits, but even these maintain stable configurations over long timescales. The predictability of planetary orbits allows precise calculations. Astronomers can determine exactly where planets were at any date in the past or where they'll be in the future. This precision enables spacecraft navigation, allowing missions to be planned years in advance with confidence that both spacecraft and target planet will arrive at the correct location at the appointed time. It also allows accurate prediction of eclipses, planetary alignments, and other celestial events centuries in advance. This orbital harmony provides the stable foundation necessary for life. Earth has remained in the habitable zone, the region where liquid water can exist, for billions of years. The seasons follow predictable patterns year after year. Day length remains essentially constant. These stable conditions allowed life to emerge and evolve without facing catastrophic environmental disruptions caused by orbital instabilities. The patient, reliable motion of planets creates cosmic environments where complexity can develop and persist. Throughout the observable universe, billions of galaxies shine quietly across vast distances. These distant systems have been glowing for billions of years, their light streaming steadily through space toward telescopes on Earth. Most galaxies are so far away that their appearance changes imperceptibly from one human generation to the next. They simply persist, following their own evolutionary paths, forming stars, hosting planets, and gradually changing over cosmic timescales. The light from the most distant galaxies has been travelling for over 13 billion years, showing us these systems as they appeared when the universe was young. These galaxies didn't know their light would eventually reach Earth. They simply continued their existence, shining steadily into the cosmic darkness, following the same physical laws that govern all matter and energy in the universe. When you look at a distant galaxy through a telescope, you're seeing it as it existed long ago. A galaxy 1 billion light-years away appears as it was 1 billion years in the past. A galaxy 10 billion light-years away shows itself as it existed 10 billion years ago, when the universe was only about a quarter of its current age. The most distant galaxies visible to our most powerful telescopes appear as they were over 13 billion years ago, less than a billion years after the Big Bang. These distant galaxies often look different from nearby ones. Young galaxies tend to be smaller, more irregular in shape, and undergoing more vigorous star formation than their modern counterparts. They contain more gas available for forming stars and fewer of the heavy elements produced by stellar nucleosynthesis. Observing galaxies at various distances allows astronomers to study cosmic evolution directly, seeing how galaxies change over billions of years. The light from these galaxies has been travelling toward Earth for most of cosmic history. During its journey, the universe expanded, stretching the wavelength of the light and shifting it toward the red end of the spectrum. This cosmological redshift provides a direct measure of distance. The more redshifted a galaxy's light, the farther away it is, and the longer its light has been travelling. Some galaxies are so distant that their light has been redshifted from visible wavelengths into the infrared. What started as blue or ultraviolet light from hot young stars has been stretched to wavelengths longer than the human eye can detect. Infrared telescopes like the James Webb Space Telescope can observe these deeply redshifted galaxies, revealing the universe's earliest luminous structures. Most galaxies visible in deep telescope images are billions of light-years away. A typical deep field image might show thousands of galaxies, each one a system containing hundreds of billions of stars, each potentially hosting its own planets. The galaxies appear as faint smudges or small ellipses, but each one represents an enormous cosmic structure comparable to or larger than our Milky Way. These distant galaxies evolve slowly from our perspective. A galaxy 5 billion light-years away would need millions or billions of years to show noticeable changes in structure. Over a human lifetime, it appears essentially frozen, unchanging. Yet it continues its existence, forming new stars, perhaps merging with neighbours, gradually evolving according to the same physical processes that shape all galaxies. The steady persistence of these galaxies is reassuring. They weren't created for our observation. They don't exist to send their light toward Earth. They simply exist, following the laws of physics, shining because they contain stars, evolving because gravity organizes matter. The fact that their light eventually reaches us is almost coincidental, a consequence of the finite speed of light and the vast size of the universe. You don't need to remember these distances or these timescales. Just let the thoughts settle peacefully in your mind. Each galaxy represents billions of years of cosmic history, countless stellar births and deaths, potentially trillions of planets. They continue their existence whether we observe them or not, steady and persistent across the cosmos. The universe operates on timescales that dwarf human experience, and this vastness provides a unique sense of perspective. Stars live for millions or billions of years. Galaxies evolve over even longer periods. The universe itself is about 13.8 billion years old. When viewed against these cosmic timescales, the concerns and worries of daily life seem smaller, less urgent. There's comfort in knowing that the universe has existed for so long and will continue for so much longer. The sun will keep shining for billions of years. The stars will continue their patient journeys through the galaxy. These vast timescales remind us that change happens gradually in the cosmos, that stability and persistence are fundamental features of the universe. Everything unfolds according to its own rhythm, without hurry or anxiety. Consider the lifespan of a typical star like our Sun. It formed about 4.5 billion years ago, and will continue shining for roughly another 5 billion years. That's a total lifetime of about 10 billion years. During this time, it maintains remarkable stability, converting hydrogen to helium at a steady rate, providing constant warmth and light. 10 billion years is nearly as long as the universe has existed. It's long enough for a planet to form, for life to emerge, for evolution to create complex organisms, for civilizations to rise and fall multiple times. Larger stars live shorter lives. A star 10 times the Sun's mass might live only 20 million years before exhausting its fuel. Yet even 20 million years is an almost incomprehensible span of time, longer than the entire existence of human species. Smaller stars live much longer. A red dwarf star with 1/10 the Sun's mass might shine for 10 trillion years, 1,000 times longer than the universe's current age. These stars will outlive everything else in the cosmos, still glowing long after all other stars have faded. Galaxies evolve over billions of years. The Milky Way has existed for most of cosmic history, probably forming within the first billion years after the Big Bang. It has grown through countless mergers, gathered material from its surroundings, formed hundreds of billions of stars, and continuously evolved its structure. Yet all these changes happened gradually, taking millions or billions of years for each significant transformation. The galaxy will continue evolving for billions of years into the future, slowly changing but never rushing. The universe itself provides the ultimate perspective on time. 13.8 billion years have elapsed since the Big Bang. That's enough time for the first atoms to form, for the first stars to ignite, for galaxies to assemble, for countless generations of stars to live and die, for heavy elements to accumulate, for planetary systems to form, for life to emerge and evolve into consciousness capable of contemplating cosmic history. All of this happened gradually, step by patient step, over timescales that make human history seem like a brief instant. Looking forward, the universe will continue for an almost unimaginable duration. The sun will keep shining for 5 billion years. Stars will continue forming for trillions of years. Even after star formation ceases, existing stars will shine for additional trillions of years as they slowly cool. The universe shows no sign of ending anytime soon. It will persist, evolving gradually for timescales that dwarf even the billions of years that have already passed. These vast timescales create a sense of cosmic patience. Nothing in the universe hurries. Stars take millions of years to form. Planetary systems require billions of years to develop life. Galaxies merge over hundreds of millions of years. Everything proceeds at its own pace, determined by physical laws, uninfluenced by urgency or impatience. The universe simply exists and evolves according to its own deep rhythms. There's something deeply calming about this perspective. Your concerns, your worries, your daily anxieties exist on timescales of hours, days, or years. Set against cosmic timescales, they're fleeting moments, brief ripples on a vast ocean of time. This doesn't diminish their importance to you, but it does provide perspective. The universe has seen billions of years pass and will see billions more. It continues its patient unfolding, stable and enduring, a constant presence that transcends all temporary troubles. Light carries momentum, and when photons strike a surface, they exert a tiny pressure. This radiation pressure is gentle but measurable, and it plays important roles throughout the universe. In stars, radiation pressure from the intense light produced in their cores helps balance the inward pull of gravity, maintaining stellar stability. Around young stars, radiation pressure can push dust particles outward, helping to clear the inner regions of planetary systems. On much larger scales, the pressure from starlight contributes to the dynamics of interstellar clouds. Though this pressure is extraordinarily weak by everyday standards, its persistent nature allows it to influence cosmic structures over long time periods. This gentle push of light is yet another example of the subtle forces that shape the universe, working patiently over billions of years to create the cosmos we observe. Radiation pressure arises from a fundamental property of light. Though photons have no mass, they carry momentum. When a photon strikes a surface and is absorbed or reflected, it transfers its momentum to that surface, creating a tiny push. For a single photon, this push is infinitesimally small, far too weak to detect. But when countless photons strike a surface continuously, their combined pressure becomes measurable. In the Sun's core, radiation pressure plays a crucial role in stellar stability. Nuclear fusion generates enormous amounts of energy in the form of gamma-ray photons. These high-energy photons push outward against the overlying layers of the star. This outward pressure balances the inward pull of gravity, maintaining hydrostatic equilibrium. Without radiation pressure, gravity would cause the Sun to collapse. Without gravity, radiation pressure would cause the Sun to expand. The precise balance between these forces keeps the Sun stable at its current size. This balance becomes even more critical for massive stars. In stars many times more massive than the Sun, radiation pressure provides most of the support against gravity. The intense energy production in their cores generates such powerful radiation that it nearly balances gravity on its own. The most massive stars exist near a stability limit, where radiation pressure almost overcomes gravity. If they were much more massive, radiation would blow them apart. Radiation pressure also influences the formation of planetary systems. When a star first forms, it's surrounded by a disk of gas and dust from which planets will eventually form. The young star's intense radiation pushes small dust particles outward, helping to clear the inner regions of the disk. Larger particles and clumps of matter experience less radiation pressure relative to their mass, allowing them to remain in place and grow into planets. This selective pressure helps establish the structure of planetary systems, with small particles swept outward and larger bodies remaining closer to the star. On interstellar scales, radiation pressure from many stars collectively influences the dynamics of gas clouds. When massive stars form within a cloud, their intense ultraviolet radiation and stellar winds push on the surrounding gas, compressing some regions and dispersing others. This can trigger new waves of star formation in compressed regions, while preventing star formation in dispersed areas. Over millions of years, radiation pressure from generations of stars sculpts the structure of the interstellar medium. Comets experience radiation pressure as they approach the Sun. Sunlight pushes on the dust and gas released from the comet's nucleus, creating the characteristic dust tail that always points away from the Sun regardless of the comet's direction of motion. This visible demonstration of radiation pressure has been observed for centuries, though the mechanism wasn't understood until the development of electromagnetic theory. Spacecraft can use radiation pressure through solar sails, large reflective surfaces that catch sunlight and convert its pressure into propulsion. Though the acceleration is tiny, it's continuous and requires no fuel, allowing spacecraft to gradually build up significant speeds over months or years. Several spacecraft have successfully used solar sails for propulsion, demonstrating that radiation pressure, though gentle, is real and useful. The pressure from starlight reminds us that light isn't merely something to observe. It's something physical, carrying energy and momentum capable of pushing matter and influencing cosmic structures. This gentle pressure operates continuously throughout the universe, contributing to stellar stability, shaping planetary systems, and sculpting interstellar clouds. It works patiently, persistently, one photon at a time, accumulating over vast timescales to create measurable effects on the cosmos. According to Einstein's general relativity, space and time form a unified fabric called space-time that can be curved by mass and energy. This curvature is what we experience as gravity. In most regions of the universe, space-time is gently curved, creating smooth gravitational fields that guide the motion of planets and stars. Earth's gravity curves space-time just enough to keep the Moon in orbit and to hold the atmosphere in place. The Sun's more substantial mass creates a deeper curvature that keeps all the planets in their orbits. These gravitational wells are stable and predictable, like gentle valleys in the landscape of space-time. Objects follow the natural curves of this landscape, moving along paths called geodesics. This geometric view of gravity reveals the universe as a smooth, continuous structure where matter and energy glide along predetermined curves through four-dimensional space-time. Einstein's theory, published in 1915, revolutionized our understanding of gravity. Rather than thinking of gravity as a force pulling objects together, general relativity describes it as a geometric property of space-time itself. Massive objects create curves in the fabric of space-time, and other objects simply follow these curves, moving along the straightest possible path through the curved geometry. Imagine space-time as a flexible surface, like a stretched rubber sheet. Place a heavy ball on the sheet, and it creates a depression. A smaller ball rolling nearby will naturally curve toward the depression, not because the large ball is pulling it, but because the surface itself is curved. This analogy helps visualize how mass curves space-time, though the real situation involves 4 dimensions rather than 2, making it more difficult to picture directly. Earth's mass creates a modest curvature in the space-time around it. This curvature keeps the Moon in its orbit and holds the atmosphere close to the surface. Objects falling toward Earth are simply following the curved paths through space-time created by Earth's mass. They're not being pulled in the traditional sense, they're moving along geodesics, the straightest possible path through curved space-time. The Sun creates a much deeper curvature because of its greater mass. The planets orbit the Sun by following geodesics through this curved space-time. From the planet's perspective, they're moving in straight lines. It's the curvature of space-time that makes their paths appear circular when viewed from outside. This elegant geometry explains why planetary orbits are so stable and predictable. They're simply following the natural contours of the space-time landscape. Light also follows geodesics through curved space-time. When light passes near a massive object like the Sun, its path bends slightly, an effect called gravitational lensing. This bending was first observed during a solar eclipse in 1919, providing one of the earliest confirmations of general relativity. The effect is usually small, but near very massive objects like galaxy clusters or black holes, the bending becomes substantial, creating multiple images or distorted arcs of background galaxies. In most of the universe, space-time curvature is gentle and smooth. There are no abrupt changes, no sharp edges in the gravitational landscape. The curvature created by stars and planets produces stable gravitational wells that persist for billions of years. Objects orbiting within these wells follow predictable paths determined entirely by the geometry. Even the expansion of the universe can be understood in terms of space-time geometry. The universe isn't expanding into anything. Rather, space-time itself is stretching, increasing the distances between galaxies. This expansion follows equations that describe how space-time evolves, connecting the geometry of the universe to its matter and energy content. The beauty of general relativity lies in its geometric simplicity. Mass and energy curve space-time. Curved space-time guides the motion of mass and energy. This creates a self-consistent framework where everything influences everything else through the geometry of space-time. The mathematics is complex, but the underlying concept is elegant. The universe is a four-dimensional geometric structure, smoothly curved by the presence of matter and energy, with all objects following the natural contours of this curved landscape. This geometric view provides a sense of cosmic order and inevitability. Planets orbit stars because they're following geodesics through a curved space-time. Galaxies cluster together because their combined mass creates deep gravitational wells. Light bends near massive objects because space-time itself is curved. Everything follows from the geometry, creating a universe that operates according to comprehensible mathematical principles. A calm, ordered cosmos where motion and structure arise naturally from the elegant curvature of space-time itself. When stars like our Sun exhaust their nuclear fuel, they shed their outer layers and leave behind a hot, dense core called a white dwarf. These stellar remnants are no longer generating energy through fusion. Instead, they simply radiate away their stored heat, cooling gradually over billions of years. A white dwarf might start with a surface temperature of 100,000 degrees Celsius, but it will slowly cool to a few thousand degrees, then eventually to even lower temperatures. This cooling process is extraordinarily slow, taking longer than the current age of the universe for a white dwarf to cool completely. The universe isn't old enough yet for even the oldest white dwarfs to have cooled all the way down. These patient embers of former stars will continue cooling for trillions of years, eventually becoming cold, dark remnants that no longer emit visible light. A white dwarf forms when a star like our Sun reaches the end of its main sequence life. After exhausting the hydrogen in its core, the star expands into a red giant, then gradually sheds its outer layers, creating a planetary nebula. What remains is the star's core, compressed to extraordinary density. A white dwarf with the mass of the Sun would be about the size of Earth, making it roughly 1 million times denser than the Sun's average density. This extreme density arises from electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being compressed further. Unlike normal matter where atoms have structure and empty space, white dwarf matter consists of atomic nuclei surrounded by a degenerate gas of electrons packed as tightly as quantum mechanics allows. This degeneracy pressure, not thermal pressure, supports the white dwarf against further gravitational collapse. A newly formed white dwarf is extraordinarily hot, with surface temperatures reaching 100,000 degrees Celsius or higher. The interior is even hotter, retaining heat from the star's former fusion processes. But with no ongoing fusion to generate new energy, the white dwarf can only cool, radiating its stored thermal energy into space as light and heat. The cooling process is slow because white dwarfs have enormous heat capacity. Despite their small size, they contain enough thermal energy to shine for billions of years. A white dwarf cools rapidly at first, dropping from 100,000 degrees to perhaps 20,000 degrees in the first few 100 million years. But the cooling rate slows over time as the temperature drops. After about 1 billion years, a white dwarf might cool to around 10,000 degrees, similar to the surface temperature of many main sequence stars. It would still glow white or bluish-white, hot enough to emit visible light. After 10 billion years, roughly the current age of the universe, it might cool to 5,000 degrees, glowing with a reddish or orange colour. The oldest white dwarfs in our galaxy, formed soon after the first stars appeared, have cooled to about 4,000 degrees after more than 12 billion years. Cooling continues inexorably. Eventually, after hundreds of billions or trillions of years, white dwarfs will cool below 3,000 degrees, becoming too faint to emit significant visible light. At this point, they're sometimes called black dwarfs, though no black dwarfs exist yet because the universe isn't old enough. These cold stellar remnants would be nearly invisible, detectable only by their gravitational influence or perhaps by faint infrared radiation. The eventual fate of most stars resembles this patient cooling. Stars with masses up to about 8 times the Sun's mass will end as white dwarfs. More massive stars explode as supernovae, leaving behind neutron stars or black holes, but these are relatively rare. Most stars follow the peaceful path from main sequence to red giant to planetary nebula to white dwarf, then spend trillions of years slowly cooling in the darkness. White dwarfs represent a kind of stellar immortality. Though no longer truly alive in the sense of generating energy through fusion, they persist for timescales longer than any other stellar remnant. Neutron stars cool more quickly due to neutrino emission. Black holes persist eternally but emit no light. White dwarfs, glowing faintly with their stored heat, will be among the last objects to shine in the far future universe. Patient embers of long-dead stars, cooling slowly toward absolute zero but never quite reaching it. Enduring monuments to stellar lives that ended billions or trillions of years earlier. Several planets in our solar system possess ring systems, and Saturn's rings are the most spectacular. These rings consist of countless particles of ice and rock, ranging in size from tiny grains to house-sized chunks, all orbiting the planet in a thin disk. The rings appear solid from a distance, but they're actually composed of individual particles, each following its own orbit around Saturn. The system is remarkably flat, extending hundreds of thousands of miles across but only about 30 feet thick in some regions. The rings are stable structures that have existed for millions of years, maintained by the gravitational influence of Saturn and its moons. They reflect sunlight beautifully, creating one of the most peaceful and elegant sights in the solar system. Ring systems demonstrate how gravity can organize matter into graceful, long-lasting structures. Saturn's rings extend from about 7,000 miles above the planet's equator to about 80,000 miles outward, spanning a distance wider than the gap between Earth and the Moon. Yet despite this enormous extent, the rings are extraordinarily thin. In most regions, the ring thickness is only about 30 feet, making the rings proportionally thinner than a sheet of paper is wide. The rings consist primarily of water ice, with some rocky material mixed in. Individual particles range from microscopic grains to chunks as large as houses or even mountains. Most particles are probably between a few inches and a few feet across. Each particle orbits Saturn independently, following Kepler's laws of planetary motion. Particles closer to Saturn orbit faster than those farther out, creating differential rotation across the ring system. The rings appear continuous from Earth, but spacecraft observations reveal intricate structure. The rings are divided into several main sections, labelled alphabetically in order of discovery. The A ring and B ring are the brightest and most visible. Between them lies the Cassini division, a gap about 3,000 miles wide where particle density is much lower. The C ring lies inside the B ring and appears more transparent. Fainter rings extend both inward and outward from the main visible rings. This structure arises from gravitational interactions with Saturn's moons. Moons orbiting near the rings create gravitational resonances that clear gaps or enhance certain regions. The Cassini division, for example, is maintained by gravitational resonance with the moon Mimas. Particles in the division would have orbital periods that are simple fractions of Mimas's orbital period, and these resonant particles are gradually cleared out by repeated gravitational tugs from the moon. Small moons called shepherd moons help maintain sharp edges to some rings. These moons orbit just inside or outside ring boundaries, and their gravity nudges ring particles back into line, preventing the rings from spreading. The F ring, a narrow feature just outside the A ring, is maintained by two shepherd moons, Prometheus and Pandora, orbiting on either side. The origin of Saturn's rings remains somewhat uncertain. They might be remnants from Saturn's formation, material that was prevented from coalescing into a moon by tidal forces from the planet. Alternatively, they might be debris from a moon or comet that was torn apart by tidal forces after passing too close to Saturn. The relatively bright appearance of the rings suggests they might be younger than Saturn itself, perhaps only a few 100 million years old, though this remains debated. Other planets also have rings, though none as spectacular as Saturn's. Jupiter has faint rings composed of dark dust, discovered by the Voyager spacecraft. Uranus has narrow dark rings, quite different from Saturn's broad bright rings. Neptune has several faint rings, including some incomplete arcs. Even some asteroids have been found to possess tiny ring systems. All these rings demonstrate the same basic principle. When particles orbit within a certain distance from a massive body, tidal forces prevent them from coalescing, and they form stable ring structures instead. Saturn's rings will not last forever. Gravity from Saturn slowly pulls ring material inward, and some material is lost to the planet's atmosphere. Current estimates suggest the rings might disappear within a few 100 million years, though new material from impacting comets or disrupted moons might replenish them. For now, they endure, a graceful structure maintained by the delicate balance between orbital motion and gravitational influence, reflecting sunlight in a peaceful display that has captivated observers since Galileo first glimpsed them through his telescope in 1610. 4 fundamental forces govern the universe: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. These forces work together harmoniously to create the cosmos we observe. Gravity shapes the large-scale structure of the universe, gathering matter into stars, planets, and galaxies. Electromagnetism binds atoms together and creates the light we see. The strong nuclear force holds atomic nuclei together, allowing elements to exist. The weak nuclear force enables certain types of radioactive decay and plays a role in stellar processes. These forces operate simultaneously, each in its own domain, without conflict or interference. They've maintained this balance since the universe began, working together to create stable atoms, long-lasting stars, and persistent galaxies. This cooperative relationship between fundamental forces is what makes the universe comprehensible and predictable, allowing matter and energy to organize into the beautiful structures we observe. Gravity is the most familiar force, governing motion on cosmic scales. It holds you to Earth's surface, keeps the moon in orbit, binds the solar system together, and organizes galaxies into clusters. Gravity is always attractive, never repulsive, and it acts on all matter and energy equally. Though it's the weakest of the 4 fundamental forces, it dominates at large scales because it acts over unlimited distances and always adds up, with more mass creating stronger gravitational fields. Electromagnetism governs interactions between charged particles. It binds electrons to atomic nuclei, creating stable atoms. It holds atoms together in molecules through chemical bonds. It produces light and all other forms of electromagnetic radiation. Electromagnetism can be attractive or repulsive depending on the charges involved. Unlike gravity, electromagnetic forces can cancel out when positive and negative charges balance, which is why large objects are electrically neutral despite containing enormous numbers of charged particles. The strong nuclear force binds protons and neutrons together in atomic nuclei. Without this force, nuclei would fly apart due to electromagnetic repulsion between positively charged protons. The strong force is enormously powerful at very short ranges, about 1/10 trillionth of a meter, but it drops off rapidly at larger distances. Within atomic nuclei, It overwhelms electromagnetic repulsion, creating stable configurations that can persist for billions of years, or even indefinitely for the most stable nuclei. The weak nuclear force is responsible for certain types of radioactive decay and plays a crucial role in stellar fusion. In the Sun's core, the weak force allows protons to convert into neutrons through a process called beta decay, enabling the fusion reactions that power the Sun. The weak force is stronger than gravity but much weaker than electromagnetism or the strong force. It operates only at extremely short ranges, even shorter than the strong force. These four forces complement each other perfectly. The strong force binds quarks together to form protons and neutrons, and it binds these particles together to form nuclei. Electromagnetism binds electrons to nuclei to form atoms and molecules. Gravity gathers atoms and molecules into planets, stars, and galaxies. The weak force enables the transmutation of elements, allowing stars to shine and creating the chemical diversity necessary for complex structures. The forces maintain different domains. Gravity dominates at astronomical scales. Electromagnetism governs atomic and molecular scales and produces radiation. The strong and weak forces operate only within atomic nuclei. This division of labor allows each force to perform its role without interfering with the others. Stars can fuse elements in their cores through the strong and weak forces, while being held together by gravity and emitting light through electromagnetism. The balance between these forces is remarkably precise. If the strong force were slightly weaker, atomic nuclei would be unstable and atoms couldn't exist. If it were slightly stronger, hydrogen would all fuse into heavier elements immediately after the Big Bang, leaving no fuel for stars. If electromagnetism were stronger or weaker, chemical bonds would be too strong or too weak for complex chemistry. If gravity were stronger, stars would burn out quickly. Weaker, and they might never ignite fusion. These words can drift through your mind gently. There's nothing you need to remember. The universe works because these forces cooperate, each contributing its part to cosmic structure and evolution. They've maintained this cooperative relationship since the universe began, allowing matter to organize into atoms, stars, galaxies, and ultimately into living, thinking beings capable of understanding the forces themselves. This harmonious coexistence is one of the universe's most profound features, a cosmic cooperation that makes existence itself possible. Matter in the universe is constantly recycled, moving through a cosmic cycle that has been continuing for billions of years. Stars form from clouds of gas and dust, live their lives fusing elements in their cores, then return much of their material to space when they die, either gradually through stellar winds or suddenly in supernova explosions. This returned material mixes with the interstellar medium, eventually becoming part of new clouds that collapse to form new stars and planets. The atoms in your body were created in stars that died long before our solar system formed. These atoms have been through multiple cycles of stellar birth and death. Everything you see around you, the air, the water, the rocks, the living things, all consists of recycled stardust. This cosmic recycling connects everything in the universe, creating a continuous flow of matter from one generation of stars to the next, a patient process that will continue for trillions of years. The cycle begins with the formation of stars from interstellar clouds. These clouds contain mostly hydrogen and helium, the primordial elements created in the Big Bang, along with small amounts of heavier elements from previous generations of stars. Gravity pulls the cloud together, and a new star ignites, beginning its life of nuclear fusion. During its lifetime, a star fuses hydrogen into helium in its core. For massive stars, fusion continues through successive stages, creating carbon, nitrogen, oxygen, and heavier elements up to iron. Each fusion reaction releases energy that keeps the star shining. These heavier elements accumulate in the star's core and outer layers, enriching the star's composition beyond the simple hydrogen and helium it started with. When a star dies, it returns much of this enriched material to space. Sun-like stars shed their outer layers gradually through stellar winds during the red giant phase, then more dramatically when they expel their envelope to form a planetary nebula. Massive stars die in supernova explosions, violently ejecting their outer layers along with newly formed elements created in the explosion itself. Elements heavier than iron, including gold, platinum and uranium, are primarily formed during these supernova explosions. This ejected material mixes with the interstellar medium, the diffuse gas and dust between stars. Over time, it disperses throughout the galaxy, enriching the medium with heavier elements. When new molecular clouds form and collapse to create the next generation of stars, they incorporate this enriched material. Each successive generation of stars begins life with a slightly higher abundance of heavy elements than the previous generation. Our solar system formed from such enriched material about 4.5 billion years ago. The cloud that collapsed to form the Sun and planets contained not just hydrogen and helium, but also carbon, oxygen, silicon, iron, and trace amounts of nearly every other element. These heavier elements came from stars that died billions of years earlier, possibly from hundreds or thousands of different stars whose contributions mixed together in the interstellar medium. The planets, including Earth, formed primarily from these heavier elements. Rocky planets like Earth consist mostly of silicon, oxygen, iron, and other elements forged in stellar cores. The water in Earth's oceans contains hydrogen from the Big Bang and oxygen from stellar fusion. The air you breathe contains nitrogen and oxygen from stars. Every breath you take connects you to the cosmic cycle. The atoms in your body tell the same story. The carbon in your cells was created in red giant stars through helium fusion. The oxygen you breathe was made by massive stars fusing carbon. The calcium in your bones came from stellar nucleosynthesis. The iron in your blood was forged in stellar cores. Even the trace elements, the iodine in your thyroid, the zinc in your enzymes, the copper in your blood vessels, all were created in stars and distributed through space by stellar death. These atoms have been recycled multiple times. The galaxy is about 13 billion years old, and multiple generations of stars have lived and died during this time. An atom in your body might have been part of several different stars before joining the cloud that formed the solar system. It might have spent billions of years drifting through interstellar space been incorporated into previous planetary systems returned to space when those systems' stars died, and finally found its way into the molecular cloud that became our solar system. This recycling will continue into the distant future, trillions of years from now, long after the sun has died and Earth has been destroyed or transformed. The atoms that currently make up our planet and everything on it will have dispersed back into space. Some will join new molecular clouds and become part of future stars and planets. Others might drift through space for eons. But the cycle will continue, matter flowing from stars to space to new stars, connecting past, present, and future in an endless cosmic dance. And now, the vastness of the cosmos begins to gently fade behind your thoughts. You have drifted through peaceful wonders tonight, from the ancient starlight reaching your eyes to the patient recycling of stardust across billions of years. You have explored the gentle rotation of Earth beneath your feet, the protective embrace of our atmosphere, and the moon's calming influence overhead. You have witnessed the steady rhythm of celestial orbits, the quiet journey of photons through space, and the peaceful depths between the stars. You have seen how stars form slowly in nebulae, how our sun has shone steadily for billions of years, and how the cosmic microwave background fills all space with its ancient gentle glow. You have followed the spiral arms of galaxies, the patient dance of binary stars, and the soft beauty of planetary nebulae. You have learned of constellations drifting slowly through time, the protective void between stars, and the gradual evolution of all cosmic structures. You are part of this cosmic story. The atoms in your body were forged in stars billions of years ago. The oxygen you breathe, the carbon in your cells, the calcium in your bones, all were created through stellar fusion and returned to space when those stars ended their lives. Everything within you shares a connection with the universe itself, linking you to the patient cycles that have shaped the cosmos since its beginning. Tonight, as you rest, the cosmos continues its quiet unfolding. Stars are forming in distant nebulae. Light is travelling across space. Planets are orbiting their stars with perfect reliability. Galaxies are drifting through the darkness, following ancient paths. And through it all, the fundamental forces work together in gentle harmony, maintaining the balance that makes existence possible. You are held safely within this vast, peaceful universe, a warm presence resting among the stars. The cosmic rhythms continue their patient flow, unhurried and eternal, while you drift peacefully towards sleep. Thank you for journeying through the cosmos tonight. May these gentle truths carry you softly into rest. Sleep well and dream peacefully beneath the stars. Good night.